All right. Hi, everyone. I'm Mingxun Zhou. I'm a fourth-year Ph.D. at CMU. I'm affiliated with Scilab. And today I want to talk about our new work on proof of compliance for anonymous unlinkable messages. And this is a joint work with my advisors, Elaine and Julia. So, can I click? The main motivation for our work is that privacy-preserving systems can be abused by malicious users, and there are several examples. For example, in anonymous voting, a malicious voter can have repetitive ballots, or they can even have fake identities so that they can bias the voting outcome, which is something that we definitely don't want to have. And also, because today is like a blockchain symposium, blockchain summit, we also care about anonymous transaction system. And in blockchain, there are several examples like Monero, like Zcash, and they are usually being criticized for allowing money laundering, and they are also used to sponsor adversarial entities. And one of the notable examples is that Tornado Cash, which is a coin mixer on top of Ethereum, basically it provides an anonymous transaction system that it is sanctioned by the United States government in August 2022 due to the reason that the Department of Treasury found that the North Korea hacker is actually using this system to do money laundering. So the question here is that, can we enforce some compliance checking in these kind of anonymized system while keeping honest players' privacy? To make the problem more clear, let's get to see our formalized system model. So this is our abstract model. So essentially, we assume there's multiple clients, and each client will have multiple data items, or we call them messages. And we have a shuffler, which in practice, the shuffler can be implemented by anonymous router or Tor network, something like that. So the model says, every client, they will first send their messages or their data items to the shuffler, and then the shuffler will shuffle all the things and send a shuffled set to the server. So basically, the server can only see those shuffled data items. And the goal here is that we want to have some compliance checking such that we want to check whether each client submission satisfies some predicate P. If there's any client that its submission doesn't satisfy that predicate P, we want to identify that client. So that's the goal we are trying to achieve here. To give you some more concrete ideas, here are some examples. Let's say we talk about anonymous voting. So imagine that in a voting setting where we have multiple candidates, and we want each client or each user to vote for 3 candidates. But the rule here is that we don't want any client to vote for the same candidate multiple times. So that's a rule we're trying to enforce here. And notice that this rule, it cannot be enforced based on a single ballot, because a single ballot, it doesn't make sense to talk about like repetitive ballots on a single ballot. It only makes sense when we talk about all the ballots from the single client, okay? And there's another example. This is more related to the blockchain setting. We want to have some anti-money laundering in an anonymous transaction system. So here we have like a very, very abstract representation of some anonymous transaction system. So we imagine that there are multiple clients, and each client, they could have multiple transactions, and they're going to send their transaction through some anonymous router to a blockchain node, and then the blockchain node can execute those transactions and post the hashes of those transactions to the blockchain. So ultimately, the blockchain as although it's a blockchain is a distributed protocol, we can somehow think about that as like a abstracted central party that the blockchain only sees the hashes of those transactions. So the blockchain doesn't get to see the plain text transaction from each client. The blockchain only sees the hashes. So the rule here is a very, very common anti-money laundering rule, such that we want to enforce each single client can send only up to $10,000 to the same recipient within 1 day. We could also have some other anti-money laundering rules, like you cannot send money to the recipient within some block or terrorist list, something like that. Now these are the rules we are trying to enforce in anonymous systems. Cool. And now let's get to talk about our solution. How do we do privacy preserving compliance checking in these kind of systems? So our solution is called Shuffle ZKP. It consists of 3 phases. So the first phase is the abstract message collection phase, which is common in all kinds of anonymous systems. And the second phase is a lightweight detection phase. So the lightweight detection phase will raise an alarm if any non-compliance is detected. So if there's, for example, let's say we have 100 clients, but if any one of them is doing something wrong, then this phase will raise an alarm. But in this phase, we don't know who is doing the wrong thing. So we have the next phase. If there's no alarm detected, then we can proceed to the normal next phase. For example, we can do vote counting, or we can execute transactions, things like that. And if an alarm is actually detected, we will proceed to our next phase called the blame phase. In this phase, we will have a slightly more complicated crypto protocol. But in this phase, we can indeed identify the adversary that is doing the wrong thing. So our protocol will consist of these 3 phases. Okay. So due to time constraint, today I'm only going to focus on the middle part, which is the lightweight detection phase that can raise an alarm if any non-compliance is detected. Cool. So the cryptographic tool we are relying on is zero-knowledge proof. And everyone talks about zero-knowledge proof in the first talk during this session, but it's relatively technical, so here I just give a very, very kind of non-technical view of zero-knowledge proof. So you can think about zero-knowledge proof being something like this. So you can imagine that a client can send some sealed messages to the server. Remember that the message is sealed inside the envelope, and the server cannot see what's inside that envelope directly without the client later on open that envelope. Okay. And it can also send a zero-knowledge proof, the proof saying that the sealed message inside that envelope satisfies some condition. So why we call that zero-knowledge proof? Because when the server sees that sealed envelope and also the proof, the server only learns that the sealed message inside the envelope definitely satisfies that predicate, but except this statement, the server learns nothing about the original message sealed inside that envelope. So this is the mental model you can think about zero-knowledge proof. But in practice, zero-knowledge proof is much more complicated than this. So based on zero-knowledge proof, we can have an initial attempt to solve our problem. That is, after the message collection phase, in the detection phase, we require each client to send a zero-knowledge proof. It can send the sealed messages alongside with a proof saying that my original submissions are compliant, so don't blame me. And if any client fails to send a valid proof, then the server can detect that client, or the server simply raises an alarm. But we found that that protocol has a consistent issue, that a malicious client doesn't have to send the original messages. It doesn't need to use the same messages in the message collection phase and the detection phase. So basically, a malicious client can simply just generate some fake messages during the detection phase and simply just generate a fake proof saying that, well, my submissions are compliant. But those messages are actually, they're just fake. So how do we solve this consistent issue? So our solution is to use a polynomial equality check. So from the high level, it works like this. So essentially, we're just having a polynomial connecting all messages in those sealed messages submitted by the client. We also have another polynomial that connects all the messages seen by the server during the message collection phase. So remember that polynomial is just a curve, and we can indeed represent those messages using polynomials. And as long as those two polynomials are consistent, we can be confident to say that, well, the clients are indeed submitting consistent messages during the message collection phase and the detection phase. And in the protocol, it will work something like this. So the server will first broadcast saying that, please evaluate your polynomial at point R, and that is a random challenge point R. So the client, when they're submitting their proof, they first prove that my submission are compliant, and secondly, they also need to say that my subpolynomial evaluation on that random point is Z1. Or that is for the first client, and for the last client, it says my polynomial evaluation will be Zn. And at the end, the server can compute the polynomial evaluation from the collected message set, denoted as capital Z. It can simply just verify that the product of the subpolynomial evaluation, they multiply to capital Z. Oh, why there's like a floor. And if that check fails, then the server can simply raise an alarm saying that somebody is definitely messing up with my protocol. Someone is having like inconsistent messages. Unfortunately, we also found that this thing is not perfect. It has some privacy issues. So we realized that the server can actually do these kind of attack that it brute force to find like a subset inside of that message collection phase, saying that, oh, it seems like this subset may correspond to your subpolynomial evaluation. It means that you are definitely, you are the sender of those messages. And that leaks privacy, because we want all the honest player in the system to preserve their privacy. And it turns out that we have a surprisingly simple way to solve this privacy issue. That is, the client, when they're submitting their seal messages, they can just add some random decoys. Here, we just have like different colors of tomatoes. And the client can just submit those different colors of tomatoes to the shuffler, and the shuffler will send those tomatoes to the server. And this simple algorithm turns out to be private. That is, it actually adds a lot of difficulty to the server, that the server now thinks that it's actually too hard to find a subset corresponding to the polynomial evaluation of Z1. So theoretically, we proved that it turns out roughly constant number of decoys are enough for privacy. And in practice, around 30 to 80 decoys per client will be sufficient for a large range of applications. So I want to point out that although like, the algorithm itself is surprisingly simple, the proof is actually quite non-trivial. Cool, now let's get to talk about some experiment results. So we implement multiple applications, and here I just picked two. So this is the result for the detection phase. So I have a task called robust submission. In that task, the server wants to collect the sum of each client. They have like a secret value. The server wants to collect the sum of them. So in that scenario, our compliance checking compile to roughly 20,000 constraints in the proof system. And each client only takes 0.2 seconds to finish that detection phase. And the client communication only takes like roughly 2 kilobytes. And the server time to do the verification for across 1,000 clients, in total, it only costs the server 3.4 seconds. In another application, we check that we conduct like we implement our protocol for the transaction limit check in anonymous transaction system. That compiles to more constraints, roughly corresponding to 1 million constraints. And the client time in detection phase only takes 4 seconds. That's a little bit more, but it's still quite acceptable, because we consider those protocols will be run like only periodically, for example, per week or monthly. And the client communication is 2.2 kilobytes, and the server time also takes like roughly 3 seconds. And I don't have time to talk about the blame phase, but we want to highlight that our blame phase is also pretty efficient. that, for example, if every client has 60 messages, the blame phase only takes the client 4.6 seconds. The communication per client will be 1 megabyte. And the server time now is a little bit more, but it also takes like less than 30 seconds. And cool, here's the final slides. So we designed a protocol called Shuffle ZKP. It's for compliance checking in privacy-preserving systems. It provides like 2 privacy-preserving functions that we can do lightweight detection. And if that lightweight detection detects any non-compliance, it can proceed to the blame and inspection phase. And there are several future works we want to do. For example, can we support like dynamic participants? And we want to implement our protocol in some real applications. So thank you. All right.
Yeah, so I want to ask, is your protocol dependent on any specific proof system or any ZKP suffices?
I think different ZKPs could have, so because different ZKPs, they could have different ways of implementing a thing, especially for NISIC, some protocols, they will have common reference strings. Some protocol involve like different setup phase. But I would say, in general, our protocol is, I would say, agnostic to underlying ZKP system. We just need to implement those ZKP system inside our protocol with the correct setup.
So how does different proof system influence the efficiency of your protocol?
So for example, in our implementation, we have we use 2 underlying proof systems. We use, the first one is Groth16. Groth16 has like a per circuit setup. So basically for every single application, it has to set up, it has to prepare the preprocessing phase differently. So, but that protocol gives you like better efficiency. And in another implementation, we use Plonk. And Plonk has like a universal setup, but that protocol is slightly slower. So it really depends on like their concrete setup, like their concrete, I would say like their protocol structure and their like actual implementation.
I see. Thank you. Do we have any other question?
Oh, okay. Yeah, you can scan it. You can.
Yeah. Okay, let's thank Mingxun again.